Hey everybody, happy Monday. It's Mr. Marco with you once again. Hope you guys all had a great weekend. A couple announcements as we get started with our video today. We had homework collection number 7 posted last week, so please make sure you get that turned in as soon as possible if you have not already. And on the same note with missing assignments, please make sure that you have taken that chapter 4 summative from last week. So if you have not done that, please take it. Again, the third quarter ends at, I want to say, 2 weeks. So if we're missing that test score, our grade for the quarter is probably not going to look so good. So please make sure we get all of our missing work in, including all of our quizzes, tests, homework, so on and so forth. If you have any questions on that stuff, please let your grading teacher know. Otherwise, the game plan for today is we're going to work through 5.2.2, generalizing arithmetic sequences. I'm going to put the answers up from last week's homework first, from 5.2.1 part B, and then we're going to work through a couple problems together here. So let's jump in. First things first, again, if you want to check your answers for the homework, feel free to pause the video or check those filled in notes. Otherwise, moving on. Perfect, so here we go. We're going to start with a little warm-up. First, we're going to review the difference between arithmetic and geometric sequences. Again, we talked about that last week, Thursday, and last week, Tuesday, a little bit. So when we think about sequences, it's like an ordered list of numbers, and there's two specific types that we kind of classified on Thursday last week: arithmetic and geometric. And arithmetic is when we are adding, let's fix that quick, is when we're adding the same amount to the next term. So they're adding the same between terms. Adding the same number between terms or taking away the same amount between terms. So adding arithmetic, A and A. Adding arithmetic. Geometric is when we are multiplying by the same number in between our terms. So it's if everything's getting 2 times bigger as we go through, and that would be a geometric sequence. Again, we're multiplying, geometric, arithmetic, add, A. It's one easy way for us to remember that. So little review, which is the sequence and what is the sequence generator. So looking at our warm-up here, we have 9, 1, -7, -15. Is that going to be arithmetic or geometric? And then what is the sequence generator? How much is it growing or decreasing by? So a good way to tell this is to look at the distance between all of these numbers. So as we go from 9 to 1, that's subtracting 8. So from 1 to -7, again, we're subtracting 8. If we go from -7 to -18, again, we are subtracting 8. Again, we can think about this as like we're adding a negative number, so I think that's going to be an arithmetic sequence. Again, we're decreasing by 8, so I think our answer has got to be C for our warm-up. Awesome, so if we haven't yet, let's get our notes out. 5.2.2, let's jump into arithmetic sequences. So in lesson 5.2.1, again, we learned how to identify arithmetic and geometric sequences. Today, we're going to solve problems involving arithmetic sequences. Use the questions below to help your team stay focused and start mathematical conversations. So again, you're just watching the video, but as you're watching at home, think of the following questions. What type of sequence is this? How do we know? How can we find the equation? And is there another way that we can see it? All right, so let's start with 5.56. Sequences have their own notations and special words and phrases that help describe them, such as term and term number. So the questions below will help us learn more about this vocabulary and notation. So let's start by looking at the sequence right here. So we got -9, -5, -1, 3, 7, and we're going to answer some parts about this question. So again, is the sequence arithmetic, geometric, or neither? Kind of like we just did in our warm-up, let's take a look at the difference between these two, see if we can figure out a pattern. So between -9 and 5, we got to add 4 to get from -9 to 5. Or -5, we do the same exact thing to go from -5 to -1. Same thing from -1 to 3, we're adding 4. So I think this is going to be arithmetic, again, because we are adding the same amounts, arithmetic, A. And then how can we tell again? Because it's increasing by the same amount from in between every single term. So what's the first term in this sequence? That's the one furthest to the left. So that's going to tell us that -9 is going to be the first term in our sequence. Next, let's take a look at C. When the sequence generator adds a number to each term, that value, or the value that is added, is known as the common difference. So is the difference between each term before it, or it is the difference between each term and the term before it. So in this case, what's our sequence generator? What's our common difference? Again, I think we can tell that from looking right here. That's what we figured out the distance between every single term was. Our sequence generator here is 4, because again, we are adding 4 every time we go from left to right. Moving on, part D, we're going to record the sequence in the table. So remember, a sequence table compares the term number n to the value of each term t of n. So we're going to order these up. We start with our term number 1, then we're going 2, 3, 4, and 5. And then our t of n is the values from our sequence here. So we're starting with -9. Then we are adding 4, so we go to -5, -1, 3, and then 7 in our table. So this is similar. It's not the same as a linear equation, but it's similar in the fact that we can think of this n kind of representing our x, and this t of n is kind of like our y, where our n is our input, and our t of n, or the value of the nth term, is really like our output. So again, it's not linear, so they're not like x and y, but it's kind of similar, where that left-hand side is going to be what we're plugging into our function, the right-hand side what we're coming out of that function with. Again, kind of like our x and y respectively when we talked about functions way back at the beginning of the year and throughout the year here. So what is t of n when n is equal to 0? So what is t of n when n is equal to 0? So if we go from this spot and then we go up one more, imagine we have a 0 here. Again, I think if we're adding 4, if we go down, we got to take 4 away if we're going up 1. So if we imagine that we have 0 here, that t of n would be -13. So if we're just going back one spot in our table, we got to take 4 away. So take -9 minus 4 would be -13. So let's graph these points and see what we come up with. So we're going to start at 1, -9. I think that's the only one that's, or the first one that's going to fit on our graph. So we got 1, -9. I'll scroll back up in a second here, since my picture is going to block the graph. We got 2, -5 over 2 down 5. So perfect. As we keep plotting these points, then we go to 3, -1. That's what we got. We got 4, 3, 5, 7, and so on and so forth. So should this graph be continuous or discrete? And I'm going to say this one should probably be discrete. Because if we look at our sequence at the very top of our page, where we have -9, -5, -1, 3, and 7, these are our only outputs in that sequence. There's nothing in between those points. So because there's nothing in between those points, and we're only plugging in whole numbers like 1, 2, 3, 4, 5 into our sequence, and we're only getting out, again, these circled values of our sequence, we shouldn't fill in the dots or connect the dots, because that would mean we have a continuous function or a linear equation, which in fact we do not here, because again, the only thing that's coming out are those whole numbers that create that pattern of our sequence. So this is going to be discrete, again, because we're only getting out those certain outcomes, which is giving us our sequence. If it was continuous, then it would be a linear equation, and there would be really no pattern for us to really figure out there. So again, discrete, do not fill this in, not a continuous function, because again, it's a sequence. We're only looking at these specific outcomes in this situation. On to the next page, we're going to part G. Write an equation beginning with t of n is equal to, for the nth term of this sequence. So let's start with that. Let's go t of n is equal to, so again, like we've talked about, our sequences here are kind of like linear equations, right? Where we have that starting value of t is equal to 0, or n is equal to 0. That was -13, as we could see from our table up, or from the last page. And we know that we're adding 4 to every term. So if we think about our linear equations, which again, this is similar but not exactly the same. We have y equals mx plus b, where in this case, again, we're kind of replacing that y with t of n like we talked about on the last page. In our sequences, we're replacing x with n. So if we think about our growth as being the difference of our arithmetic sequences, like we're growing by 4 every single time, we can kind of treat that difference like our slope and say that we would have 4 times n, and then take away or add our starting value at the end, that initial value of our sequence, which in this case would be minus 13. So I apologize for the different colors if you're OCD, but t of n is equal to 4n minus 13 would be probably a good spot for us to start with our function here. So what is the domain for this sequence? Again, we're plugging in any whole number that's greater than or equal to 0. So in this case, we have n is greater than or equal to 0, which is very similar to what our domain has been written like before. And then how is the common difference related to the graph of our equation? We kind of talked about that already with part G, but it's very similar to slope. And that 4 is our common difference. And again, this is more or less the same thing as slope. So think of the common difference as the slope or growth of our sequence. All right, moving on to 57. Let's keep rolling down the page. So next we're going to look at another sequence. We've got -4 goes to -1, then -1 to 2, then 2 to 5. So the first term is t of 1, which in this case is going to tell us that that is that -4. So I'm going to write that here as t of 1 is equal to -4. What is t of 0 for this sequence? So before we do that, what's our common difference? So if we look from this term to this term, adding 3, again, we're continuously adding 3 between every single term. So our difference is 3. So if we go back one spot this way, got to subtract 3. So that would tell me that t of 0 is going to be -7. All right, so now that we know our difference, we've got t of 0 right here. Let's write an equation for t of n and see what we come up with. So again, t of n would be equal to 3 times n minus 7. So now if we want to verify that this works, let's just plug these numbers in for n, or plug numbers in for n and see what we come out with. So I'm going to make a little t-chart, or a little table. So we're going to check the first term. We got n, we've got t of n, we got 1, 2, 3, 4. So if we do t of 1, we have 3 times 1 minus 7, which is equal to 3 minus 7, equal to -4. There's our first value. T of 1 is equal to -4. So far, so good. And if we do the exact same thing 3 more times, which I would recommend you practice just for a little bit of extra practice, we're going to skip for the sake of time of the video. This does in fact work, where we get the exact same things of -1, 2, and then 5 for our function. So next, we're going to take a look at, is it possible for t of n to equal 42? T of n to equal 42. So we're saying basically, if t of n equals 4 or 42, what is n? So we've done these problems before with our function notation, so we're going to apply that same kind of logic here. So this is our function. We're going to try to solve for n. We've got 42 is equal to 3n minus 7, and now we're going to try to solve for n. So our first step, add 7 to both sides. 49 equal to 3n, divide by 3, divide by 3. So is 49 divisible by 3? No, it is not. So we're going to get into a little trouble here, because if we evaluate this, we get 16.3 repeating. And again, like I mentioned on the last page, this is discrete. So we're only plugging in integers into our sequence here. So if this n value is not a whole number, then we can't get that desired outcome. So this is not possible. Not possible for this sequence. Not possible for this sequence. All right, again, let's keep moving. If we look at D, we're asking, is for f of x equals 3x minus 7? Again, we took our sequence, basically put it into function notation. Is it possible for f of x to equal 42? Yes, that is absolutely true. And that is, again, because this is a linear equation, and those are continuous. Linear equations are continuous. Sequences are not. And linear equations can have non-integer answers. So again, that would mean that, again, we could get f of x to equal 42, and that's 16.3 that we figured out in the last equation could be a value for x because it doesn't have to be a whole number. So again, like I just kind of mentioned and talked about, the difference between t of n and f of x is that t of n can only have integers being plugged into it. For f of x, any function 9 times out of 10 is probably going to be all real numbers for our domain. We can plug in any value whatsoever for x, where again, t of n, our sequences, t of n are with our sequences, we are only plugging in integers as our inputs. So because of that, that restricts our outputs, again, makes them discrete and not continuous, like we again talked about before. All right, let's do a couple of practice problems as we move on to the next page. We're gonna do 5, 58, 60, and then 62 together for a little extra practice with our sequences. 558, Trixie wants to create an especially tricky arithmetic sequence. She wants the 5th term of the sequence to equal 11, and the 50th term to equal 371. So that is, she wants t of 11 to equal, or t of 5 to equal 11, sorry, and then t of 50 to equal 371. So is it possible to create an arithmetic sequence to fit her information? If possible, find that equation, the initial value of t0, and then the common difference for the arithmetic sequence. If not possible, explain why not. So again, here are the two things we got to find. Again, the initial value and the common difference. Again, because like we talked about before, these are very similar to linear equations. That common difference is basically like our slope. So we can think about these two values that I've got highlighted in green, the fact that it's kind of like the slope between 2 points. So that's how we're going to figure this out. Again, like we said, our t of n represents our y, more or less, and then that's what it's equal to is like the n. So again, that t of n is y. So again, this is 11 would be y, 371 would be y. The number on the inside of the parentheses is like our x. We can write our slope, or our growth in this case, using our formula, just tweaked a little bit, our point slope formula, like y2 minus y1 over x2 minus x1. Again, just knowing that we're kind of tweaking that a little bit for our sequence, but again, it's very similar in practice. So if we think about this as an ordered pair, we could say that 371 minus 11 over 50 minus 5, that's going to tell us our difference. So if we evaluate this, we're going to get 360 over 45, not 366, but that's going to tell us that our growth is going to be 8. Growth is going to be 8. So again, if we think like we had before, our y equals mx plus b, we're going to change that just a little bit, where we're going to say that we have t of n is equal to that difference times n plus our initial value. We're going to call that a sub naught. We'll talk about that more in a little bit. But anyways, that's what we're going to try to figure out. So we got our difference, we got d, we just got to figure out, again, that starting value, that a naught value. So let's figure that out. Now, since we know a point, we can just plug those numbers in and figure out that value and find the overall equation, just like we did with lines back in chapter 2. So here, let's plug in, let's say t of 5 is equal to 11. So that would mean that 11 is equal to 8 times 5, and then plus a naught. Perfect. So now we have 8 times 5. 11 is equal to 40 plus a naught. Now let's subtract 40 from both sides. So we get negative 29 is equal to a naught. So if we plug that back into this equation up on the top here, we can say that the equation for our sequence is going to be t of n equals 8 times n minus 29. So again, very similar to what we had with our linear equation problems where we're talking about the difference. It means the exact same thing as finding slope. How much is that sequence growing in between terms? And it's going to stay constant. So that's why we can think about it like slope. And again, it's more or less just plugging that number in just like we did, again, solving our linear equation problems way back in chapter 2. All right, moving back to 560. Let's keep going here. Trixie now wants an arithmetic sequence with a sequence generator of negative 17. Again, that sequence generator is telling us our difference. So again, that d is equal to negative 17. And our 16th term is 93. So t of 16 is equal to 93. Is it possible to have an arithmetic sequence that fits this? So again, if it is, we're going to find the equation. If not, we'll talk about that in just a second. So here we go. Again, our normal equation for this is t of n is equal to d times n plus a naught. Again, that initial value, that t sub 0, is just a fancy way of writing it. Again, t sub n in this case is 93. So we're going to plug in what we know and try to find our intercept. So if we've got t of n is 90, or t of 16 is 93, we can say that 93 is equal to our difference is negative 17. So we've got negative 17 times 16, and then plus that initial value a naught. So now we can evaluate this, see if we get a whole number for our intercept, or not intercept, but our starting value. And if we do, then we are in business and we actually have a sequence. So we've got 93 is equal to negative 17 times 16 is going to get us negative 272 plus that t sub 0 number. If we add that 272 to both sides, we get 365 is equal to a sub 0, which is good news because again, if we have a whole number, then we are in business. We can write our final equation for this sequence as t sub n equals minus 17n plus 365. And that is the equation that represents our arithmetic sequence there. So far, Trixie's pretty happy. We got 2 sequences that are going to work. So next, let's take a look at 62, and then we're going to wrap up for today. So Trixie's at it again. This time, she wants an arithmetic sequence that has a graph with a slope of 22. So again, she wants our difference to be equal to 22. She also wants t of 8 to equal 164, and the 13th term to have a value of 300. So that t of 13 is equal to 300. So is it possible? Why or why not? So she wants the difference to be 22. We've got 2 different points here. So I think what we should do is let's find the slope between these 2 points and see if it matches 22. And if it does, then I think we are in business. So I'm going to get rid of that, make it look a little bit neater again. 22, perfect. So our 2 points, again, change in y over change in x. These values are our y's. So let's say that 300 minus 164 over 13 minus 8 is going to be our growth. Here we get 300 minus 164 is 136. 13 minus 8 is 5. which if we evaluate that, we do not get a nice whole number, but our growth here would be 27.2. So this is what the difference between those 2 points, which this is the distance that she wants. So 22 does not equal 27.1 or 27.2. So the sequence that she wants to make is not possible. Again, because those differences do not match. And there we go. Last thing we're going to leave you with today is some toolkit stuff. So if you need a little more time filling this out, feel free to pause the video. I'm just going to talk through it really quick. The stuff that's typed in there already is stuff that we should have on our toolkit from last week. First, that exponential functions are functions that repeatedly multiply. Sequences are ordered lists of values. Sequence notation, again, that n is our term number. T of n is the value of the nth term. We can kind of think about that as n being similar to x in a linear equation. T of n is kind of similar to like f of x or y in that input-output kind of thing. Again, we talked about arithmetic sequences today, and the common difference, again, being taking any term, subtracting the previous term, or just the amount that it takes to go from one term to the next. So we have 2 examples, like 8 minus 2 is 6, 1 minus 5 is negative 4, and so on and so forth. Again, the difference between those 2 points. So last thing for today, the homework for tomorrow is the section for 522. If you have any questions, please let us know. Otherwise, hope you guys all have a great rest of your Monday, and we'll see you all in live class tomorrow.